So not only are we going to investigate acid and bases in experiment 17, but we're also going to investigate buffers. Okay, so we've talked about what is an acid, what is a base. So an acid is something that has hydrogens to donate. That's actually the definition of an acid. It's a substance that donates a hydrogen ion. Okay, and a base, the definition of a base is something that accepts a hydrogen ion. Now you might think that bases would be better defined as things that produce hydroxide in solution, OH, okay, which is essentially part of what they do, okay, but bases don't always have a hydroxide, okay, so something like this, for example, NH3, okay. NH3 is a base, ammonia. It's a base, but it doesn't have a hydroxide, right? But if you consider it in the reaction with water, then what it does is NH3 acts as the base, and it accepts a hydrogen. Where does the hydrogen come from? From water. And it becomes NH4 positive, ammonium, plus OH minus. There it is. There's the OH minus, the base that we're looking for, the hydroxide. Okay, so ammonia will produce hydroxide in solution, but it doesn't have a hydroxide to donate. Okay, but acids, for the most part, always have a hydrogen that they can just donate, that they can give off. Okay, so we're going to be looking at some acids and some bases. Learning how to measure their pHs in the laboratory, and then also we're going to be investigating some buffers. Okay, so we've learned that pH is equal to the negative log of the hydroxide H plus ion concentration, the H plus ion concentration. Okay, so if I have a 0.01 molar solution of HCl. HCl is a strong acid. The definition of a strong acid is that it will dissociate or break apart 100% of it. Okay? So HCl will dissociate into H plus Cl minus. Now we've talked about equilibrium. Equilibrium is the process of the forward reaction produces products, and then those products react to form the reactants, go backwards, right? Well, when I have just a single arrow like I do for HCl here, that means it doesn't go backwards. It means it goes to completion. This reaction will go to completion. HCl will completely dissociate. Okay? And I'll get 0.01 molar HCl, 0.01 molar H plus, and 0.01 molar Cl minus. So if I knew the concentration of the HCl, then I could determine the pH of it. What is the pH of a 0.01 molar HCl solution? Well, it produces 0.01 molar H plus. And what is the pH equal to? pH is equal to the negative of the log. What's the log of 0.01? Anybody? So if we put it into scientific notation, it'll become more obvious. 1 times 10 to the negative 2. So what's the pH? 2. What would be the pH of this HCl solution right here that we did today? 1. The pH would be 1. What would be the pH of a 0.001? 3. The pH would be 3 of that HCl solution. So if it is a strong acid, I can easily identify the H plus ion concentration because it will be equal to the strength of the acid. Okay? But not all acids are strong acids. Some acids are weak acids, like acetic acid. CH3COOH dissociates in equilibrium with CH3COO minus, which is acetate, plus H plus. So acetic acid does not donate 100% of its ions. So if it's 0.01 molar, then it is not 0.01 molar H plus. It is not. Okay? Because it doesn't pull all of the hydrogens off. Some of them come off, but then some of them go back on. They go on and off in equilibrium. There's an equilibrium that's being created for acetic acid. Acetic acid is vinegar. That vinegar that you just checked for its molarity, that's acetic acid. Okay? So this is not 0.01 molar. It is not that. Okay? Now there is a way that you can determine the molarity of that H plus ion, but that's beyond the scope of this class. You don't have to do that. Okay? All you need to really know is that that's a weak acid. So it does not dissociate 100%. But you do need to know how to calculate the pH from a strong acid. Okay? Understanding that if the molarity of the acid is 0.1, then the H plus ion concentration is also 0.1. And then I can determine the pH from that concentration. 1 times 10 to the negative 1. So the pH is 1. Okay? Well, what about when the pH is something other than 1 times 10 to the whatever? What if it was 2.78 times 10 to the negative 4 equals H plus ion concentration? Now how do I find the pH? Now I use my calculator, right? Because I can't look at this and say, oh, I know what that is. Okay? But I can say the pH is equal to the negative log of 2.78 times 10 to the negative 4. So if you have your calculators, get them out. And I want you to find the LOG log button. And then I want you to try to put in this function. Log of 2.78 times 10 to the negative 4. What is the log of 2.78 times 10 to the negative 4? Okay. So pH is equal to 3.55. Well, it comes out negative if you didn't put the negative in there. Because look, I have a negative in the front of that equation. So you'll get a negative number, then drop the negative, make it positive. pH is always positive. Okay? If you don't put the negative in the equation in your calculator, then it'll come out negative. And then you drop it and make it a positive. If you did put it in there, then you'll get a positive number, and that's what you should get. Okay? So pH is always positive. Now, I have another thing for you to try. So, if to find the pH, I need to know the H plus ion concentration. And then I can say the negative log of that, H plus, and I'll get my pH. Well, what if you were given the pH and you were asked to find the H plus ion concentration? Okay? So, 3.55 is the log, right? Now, if I put that back, I would say it's 1 times 10 to the negative 3.55. And that would be equal to my H plus ion concentration. But we do not want a number with a fraction exponent. Okay? We want a whole number exponent. So we use the function on our calculator to find out what that is. There is a button on your calculator that looks like this, 10 to the x. That is called your anti-log. It is usually a shift function of the log button. So if you hit shift log, it'll give you a 10 to the x. Okay? And if you enter 10 to the negative 3.55, what do you get? 2 point what? Okay, so we get back to where we started, right? So we get back to it. So that's how you go back and forth. So now take 2.81 times 10 negative 4 and hit log. Log of that. What's the log of 2.81 times 10 negative 4? 3.55. Now do anti-log of 3.55, negative 3.55. This is what I have my kids do when they're like, I'm bored, Dad. Log, anti-log, log, anti-log. Wouldn't you love to be my kid? Yeah. Log, anti-log, log, anti-log. Okay? Don't tell me you're bored. Find something for you to do. Okay? So, that's how you go back and forth between the H plus ion concentration and the pH. Okay? Log, anti-log. Now, the thing that people do often that is wrong is they don't put the negative back. Instead, they do 10 to the 3.55. 10 to the 3.55 is going to give you a big number. That's going to be close to somewhere in 1,000, okay? Because 10 to the third is 1,000. You don't want 10 to the third. You want 10 to the negative 3.55. You want a small number, not a big number, right? So you need that negative sign to give you that small number back. But the pH itself is written without the negative. So don't forget to put the negative back when you're doing the anti-log. Okay? All right. So what if your pOH is equal to 5.78? Can anybody tell me what the pH is? How do I find that? What is it? 8.22 is my pH. Okay? What is the OH minus ion concentration? Can anybody tell me that? You need a calculator. What is it? It's not point something. It's going to be a scientific notation number. Or it's going to be, it is point something, but definitely not 0.76. 1.05? Good. 1.05 times 10 to the negative 6. How'd you get that? 10 to the negative 5.78. The anti-log of 5.78, right? What is the H plus ion concentration here? What is H plus? Yeah. Good. Okay? That's your H plus ion concentration. Who doesn't know how we got that? Don't be shy. Okay? Do you see the 10 to the X button on your calculator? Or do you have a calculator?
I do, but I didn't get it.
You don't have, okay. Oh, you do have one?
Yes.
Okay, let's see it. I want you to use it so we can figure this out. Okay, anybody else? Is everybody else okay with how we got that? So we're going to use the anti-log button, 10 to the X, and you're going to say 10 to the negative 5.78 is going to give you your OH minus, and 10 to the negative 8.22 is going to give you your H plus, because we're going backwards. Okay, so you have to use the anti-log to get back from pH to H plus, or from POH to OH minus.
Okay, so POH, you start with 5.7, right?
Mm-hmm.
And to do your pH, you take 14 minus 578. That's when you get H2, right?
I get 8.22.
And after that, you take a log, negative log of 8.2. And that's when you get 1 over 5.
Not the negative log, you take the anti-log,
And
10 to the X,
the X.
10 to the negative 8.22.
And that's how you got the
And that's how I got this number. Okay, by taking the anti-log of those. Okay, so now if you look at your report sheet on page 241, okay, what you're going to notice is that part A, you have 4 substances, and you are going to measure the pH of those, okay, by using a pH meter and by using pH paper. So pH paper is a strip of paper that if you put it into an acid or a base solution, it changes color. And the color change that it goes to is dependent on the pH of that solution. So if it's basic, it turns yellow or it turns green. If it's acidic, it turns orange or red, okay? And it will have a chart on it. And you match the color that it turns to the chart to identify the approximate pH. Okay? And then you'll record that pH. The pH meter, very simple to use. You have it, and you put it in. You put the probe into your solution, and it gives you a readout. It says the pH is this. It's measuring the H plus ion concentration through conductivity of the H plus. Okay, so it has a probe that's measuring how conductive it is for the H plus ions that are present. All right, and that gives you the pH of the solution based on that. So you have those 4. HCl, acid, H3PO3, acid. NH3, what did we say NH3 was? NH3 is ammonium. It is it's a base. Okay? Sodium hydroxide, base. Good. Part B, we have some salts here. Now, the thing about salts is this. So, there's this thing called a conjugate acid and a conjugate base. Okay? So, for example, NH3 can become NH4 positive. This is the base. This is its conjugate acid. Bases have conjugate acids. Acids have conjugate bases. Okay? Now, if it's a strong acid, like HCl, dissociates into Cl minus. Cl minus is not necessarily a conjugate base because, even though this is an acid, because there's no equilibrium established. Okay? So to be a conjugate, you really need to have an equilibrium established. This Cl minus does not go backwards. So it's not really a base at all because it just dissociates and stays dissociated. So we wouldn't really consider it to be a conjugate base because it doesn't really act as a base. But NH3 is a base and NH4 positive is an acid. They're conjugates of one another. Okay? So we have NH4, which is the acid. We have NH3, which is a base. Okay? Other things like carbonate, CO3. It's a conjugate base in that it can become HCO3, which can then further become H2CO3. Okay? So, what is the conjugate acid of HCO3 bicarbonate? H2CO3 is the acid of it. What is the base? What is the conjugate base of H2CO3? HCO3 is the conjugate base. What is the conjugate base of HCO3? Oh, this is CO3 minus, by the way. Sorry. This is 2 minus. Forgot my charges. Okay. What is the acid of HCO3 minus? CO3 2 minus. Okay. So if I dissolve CO3 2 minus into solution, CO3 2 minus plus water, it's going to act as a base. Okay. And it's going to produce, the hydrogen is going to come from the water. It's going to become HCO3 minus plus OH minus. It's going to produce hydroxide in solution. So it is a base. CO3 2 minus is a base. And it will produce bicarbonate and hydroxide. So what would the pH be then if I'm producing hydroxide? Would it be basic or acidic? Acidic. So look at A. Sodium carbonate. What would you predict the pH to be? So this is a salt, sodium carbonate, and sodium carbonate would dissociate into Na plus CO3 minus. Those are the ions that will be present. It's a salt, so it's going to dissociate 100%. It is soluble. Okay? So you have free CO3 minus in solution, and what is it going to do? It's going to react with water, and it's going to produce OH minus. So what would you predict the pH of that one to be? Basic or acidic? It would be basic. You would predict it to be basic. You're going to measure it with the pH, and you're going to verify that. Okay? C, sodium chloride. Sodium chloride is just neutral because sodium doesn't act as an acid. Chlorine doesn't act as an acid or a base. So it just, we wouldn't predict it to have a real pH to it. It would be a neutral pH, pH of 7. Okay? Now it might not be exactly at 7, but it should be around something neutral. Okay? All right, so that's the idea is you're trying to identify. So look at B. NH4 is a what? It's a conjugate what? Acid. It's an acid, right? Well, SO4 is also a base. So you might predict, well, they might neutralize each other, okay? Or one of them is a stronger acid than the other one is a base. So if SO4 is a stronger base than NH4 is an acid, then it'll become basic. If SO4 is weaker as a base than NH4 is as an acid, then it'll become acidic. The solution will be acidic. Okay, so it'll be based on that. Your pre-lab is actually asking you to identify some of these things, like A, acid or base. How do you know? The hydrogen in front means that it's an acid. So what's the pH of that going to be? Greater than 7, right? Look at B. Acid or base? Base. So the pH will be?
Less than 7.
Oh, I'm sorry. I told you wrong on A. A should be less than 7, right? B should be greater than 7. Right? So, what about C?
No, it'd be about
So sodium is not going to act as an acid or base. And the conjugate acid of NO3 is HNO3, but HNO3 is a strong acid, meaning that it dissociates 100%. NO3 doesn't really act as a base going backwards. Okay? So it's not really gonna be sufficient. NO3, so you'll end up having more of just a neutral pH neutral there. What is it? Approximately 7. Right? Oh, well, D. How about that one? It's an acid. How about E? We've talked about that one. NH3 is it's a base. Okay, F. We have an acid, NH4, and we have a base, CO3. So if they neutralize each other, we would assume that it would be approximately 7. So we can assume maybe it's around 7. Okay. Oh, carbon dioxide. That's an interesting fellow. Carbon dioxide actually, when it dissolves in water, produces carbonic acid, which makes it acidic. So carbon dioxide will cause your solution to become acidic. And in fact, a lot of times, you know these bottles here of DI water, you guys measure the pH of the water in the lab, of the DI water, and you're like, Mr. Crown, it's like a pH of 5 or something. And you're like, that's wrong. No, it's not. The carbon dioxide in the air that dissolves into the water makes it acidic. So most water sitting out will be acidic. Okay? Because carbon dioxide produces carbonic acid in solution, and therefore it makes it acidic.
Less than 7, right?
Less than 7. Okay? Potassium acetate. Acetate is the conjugate base of acetic acid. So what does that mean about it? It's a conjugate what? Base. Which means that if you put it in solution, it will cause the solution to become
Acidic.
basic. Okay? It will cause the solution to become basic. So this is the idea behind that one. So we have KC2H3O2 dissociates into K plus C2H3O2 minus the C2H3, the K plus doesn't do anything. O2 minus reacts with water in solution and it produces acetic acid plus OH minus. So it's producing the OH minus in solution. So it is a base. So you would predict the pH to be what?
Greater than 7.
Greater than 7. Okay. Look at I.
So H is greater than 7?
Yeah, because it's a base. Look at I. What's the difference between H and I? Huh? The beginning, right? One has a potassium in the beginning. The other one has a hydrogen in the beginning. If you have a hydrogen in the beginning, what does that mean? You're an acid. This is acetic acid, right? So what is it going to do in solution? The solution will be what? Acidic. pH will be less than 7. Okay? KCl. What do you think? What's your prediction? Is K plus an acid? Is Cl minus a base? It's not going to do anything. So what's the pH? 7. Okay? That's the idea. Okay. Now, we've been talking about conjugate acids, conjugate bases. Now, if I made a solution that had a conjugate acid, 0.1 molar H, I'll just do an easy one. HF, hydrofluoric acid, and plus 0.1 molar F minus. That would mean that I had a solution with both the acid and its conjugate base present. Both of those acids and bases are present. Okay? Now, HF is a stronger acid than F minus is a base. So the solution would still be acidic, but there's a very important characteristic that it has now, which we describe as a buffer. And buffers are solutions that resist changes to pH. So if I take water and I dump some acid in it, the pH is going to drop drastically and very fast. Okay? But if I take a buffer system like this, HF and F minus, and I put some acid in it, then the pH will be maintained. It's not going to change. Why? Well, if I put acid into the solution, what can that acid react with? It can react with the base, and it will buffer out the acid. If I add base to this solution, what will it react with? It will react with the acid, and it will get rid of that extra base that I added. And therefore, the pH will be maintained. It won't change. Why? Because the changes I'm trying to make are being maintained by the buffer system. So there is a very important buffering system in our bodies. Okay? Based off of the bicarbonate. Carbonic acid, bicarbonate, and carbonate. Buffering system. So our blood has those ions in it. And if I eat my yummy sour, acidic piece of candy, then why doesn't the pH of my blood change? Well, the pH of my blood is maintained at a pH of 7.4. Why? Because of this buffering system. This buffer maintains a pH of 7.4. If my body pH changes to 7.5, I die. Okay? So it's very important that I maintain the pH of my blood. So this buffering system does that. Every time I eat my acid candy, my body says, whatever, I don't care. Yeah, go ahead. Eat that acid candy. Drink that Coca-Cola. Okay, with all of its acid H+ ions in there. Okay? Why? Because I'm just going to buffer them out. No, I'm not telling you to go drink acids and bases. That's not what I'm saying. Okay? Okay? Food quality acids and bases, fine. Okay? But don't go drink this HCl solution or whatever. Okay? That's not what I'm talking about. All right? I'm saying we buffer out food and changes all the time. pH changes all the time in our body because of this buffering system. It keeps us alive. Okay? It helps maintain that homeostasis that is necessary for us to be alive. Right? So, and it does it through this base conjugate acid vice versa situation. So the other part of this experiment, if you turn to the next page of your report sheet, is we are going to investigate the buffering system of an acid-base buffer. Okay? So first, you're going to take HCl, which is not a buffer. It doesn't create a buffer because to create a buffer, you have to be able to create an equilibrium. HCl doesn't create an equilibrium. It's just a strong acid. You're going to add, so effects of HCl on pH of a buffer. So first you're going to take some water and you're going to add drops of HCl to it and you're going to watch the pH change very quickly. With sodium hydroxide, you're going to do the same thing. Okay? Oh, that's the last part. I'm sorry. With water is the last part. The first part, you're going to take a buffer, acetic acid, sodium acetate buffer, and you're going to add the drops of HCl, and you're going to watch, and you're going to see that the pH doesn't change all that much. Yeah, it changes a little bit, but not really a lot. Compared to it, when you add the HCl to pure water, the water pH changes very quickly. But if there's a buffer present, it will be maintained. And so that's the second part of this lab that you're going to do. You're going to watch that pH of that buffer system being maintained. Okay? So that's that investigation. Okay. So that will be Monday's lab.